Hello. Today we will going to start module 3, well hydraulics. Okay. Basically, well hydraulics means the name itself suggests well hydraulics nothing but the study of water flowing towards the well. Okay. This is simply nothing but study of water flowing towards the well. Okay, it is nothing but simply the study of water flowing towards the well. Okay, if this is a well, okay, when the pumping starts, okay, when the pumping starts, if this is the initial water level, when pumping starts, okay, the water level in the well, okay, this is what water level in the well, as well as the water level in the vicinity of the well, both reduced. Okay, consider this is the initial water level. When the pumping starts, this water level reduced to this point. Okay, and also water level in the aquifer means the water level in the vicinity of the well. The water level, if this is the well, when pumping starts, water level in the well and also the water level in the vicinity of the well both get reduced. Okay, both get reduced. The reduced water level forms drawdown. Okay, the reduced water level forms drawdown. Drawdown nothing but when the pumping starts, water level in the well and also water level in the vicinity of the well, means in the surrounding the well, both water level get reduced. The reduced water level forms cone of depression. The reduced water level forms cone of depression, nothing but drawdown. So this is the drawdown curve. The reduced water level. So this is drawdown. Okay. When evaluating well hydraulics, we use the flow equation in polar coordinates. Okay, not in Cartesian coordinate. Cartesian coordinate nothing but xy, correct? Cartesian coordinate nothing but xy. Polar coordinate nothing but r comma theta. Why we prefer polar coordinate? For what reason? Means, okay, this is the top view of the well. So water level reduced in the vicinity of the well, in the surrounding well, okay, not just only in x direction or not just only in y direction, okay, in the all the direction, in radial direction also. So that's why we use when evaluating the well hydraulics, because water, once the pumping starts, water level in the vicinity, surrounding area and also in the well both get reduced, not just in x direction or not just in y direction. So water level in all the direction get reduced. So that's why we use polar coordinate system. Okay, this is the well, some angle. Okay, this is the well, this is radial direction r. Okay, once the pumping starts, water level reduced in all the direction. So that's why we use, instead of Cartesian coordinate, we use polar coordinate. Dou square h by dou x square in x direction, dou square h by dou y square in y direction equals to s by t dou h by dou t. That I'll tell you these equations in the coming derivations. So this converted into r, okay, radial direction. Okay, simply well hydraulics nothing but the study of the water flowing towards the well. Okay, this is all about well hydraulics. There are some assumptions before entering into this module. Okay, this module is having too many derivations. Okay, I'll explain you everything in detail, don't worry about it. Assumptions: the well is pumped at a constant rate. Okay, not in some variations. The well fully penetrates the aquifer. Okay, if this is the impervious layer, the well fully penetrates, not up to here or here. The well fully penetrates the aquifer. Next, the aquifer is homogeneous. The aquifer is homogeneous, isotropic and infinite horizontal extent. The well is homogeneous, isotropic, nothing but the property here is same, the property here same, the property of the soil or property of the water here same. Everything is homogeneous. Okay, so the aquifer is homogeneous, isotropic and infinite horizontal extent. Infinite horizontal area. Okay, we are not restricting to some kilometer square area. This is infinite area. Okay, these are some assumptions. Okay, aquifer is homogeneous, aquifer is isotropic and infinite horizontal extent. Aquifer is infinite horizontal area. There is no restriction, and the property of water, soil is same throughout infinite area. The property of soil and water is the same throughout infinite area. This is the meaning. Okay, next. Water is released from the storage in the aquifer, immediate response to the drawdown. Drop. Immediate response. If you start pumping, water level immediately decreases. Okay. If there is a good rain or if there is some flow from another aquifer, immediately the water level rises. Once you start pumping, water level definitely immediately reduces. If there is a good rain or if there is a flow from another aquifer, okay, if flow from another aquifer, then water level recharge, means the aquifer get recharged, the water level rises. This is immediate response, okay, to a drop in water table. Next, Darcy's law is valid. Okay, you know the Darcy's law from module 2 itself. Darcy's law, velocity V is equals to, okay, K permeability into dou H by dou T, correct? So Darcy's law is valid. These are all the some assumptions we must keep in mind throughout this module. This module mainly of derivations. Okay, in every derivation we need all these things. Okay, well, once the pumping starts, water level get reduced. Water level in the well and vicinity of the well, okay, surrounding the well, vicinity of the well, both get reduced. The reduced water level forms cone of depression, nothing but drawdown. Okay, so this is reduced water level. Okay, we can say in this fashion. Okay, and in case of well hydraulics, we prefer polar coordinate because water varies in all the direction, not only in X, not only in Y. Water level varies in all the direction. Once you start the pumping, water level varies in all the direction. Once it recharges, aquifer recharges means in all the direction it recharges the aquifer. Okay, this is all about introduction part of the well hydraulics. Hello, welcome to the new session. Today we will going to derive Thiem's equation. So first let us consider Thiem's equation, nothing but the another name for this equation, Dupit's equation. Okay, I'll tell you everything one by one. So steady radial flow to a well in an unconfined aquifer. Okay, steady radial flow to a well in an unconfined aquifer. Okay, in an unconfined aquifer or Thiem's equation, and when there is no observation well, the same equation is called as Dupit's equation. I'll tell you those things in this part. Okay. Carefully observe the diagram. Okay, this is the pumping well. Okay, these two are observation well. Right here, OB observation well 1, and this is another one, observation well 2. There are two observation well and one is pumping well. So through this pumping well, we are extracting the water, and observation well are for continuously recording the data. Okay, and this is the original water table. Once the pumping start, okay, water level slowly decreases. Once the pumping start, the original water level slowly decreasing. Okay, this is the cone of depression. Once pumping starts means water level slowly go down. So this is the cone of depression, the area of influence. Within some area the water level, that means around the pumping well, water level slowly decreases. And this is cone of depression. This is a cone of depression that shows a reduced water level. This is drawdown, SW, at the pumping well, and this is S1, drawdown at observation well 1, drawdown at observation well 2. Drawdown nothing but water level, decreased water level. Okay, and this is height from impermeable strata to the water level H1 for observation well 1, and similarly H2 for observation well 2. This is the whole head of water, H. Okay, from the center of the pumping well, radial distance R1 to the observation well 1. Similarly, from the center of the pumping well, radius R2 to the observation well 2. R1 and R2. And this is R. From the center of the pumping well to some, okay, let's say like this, small element. Okay, small, or you can take in this fashion, like this, a small element. Okay, small element, height H. Okay, and the height is small, height is dH, and distance dr, small distance. Okay, this is the radius of the pumping well, RW. Okay, from the center of the pumping well, the influence, radius of influence R to the end of the cone of depression. Okay, carefully observe the diagram. Okay, now consider steady radial flow. Okay, radial flow means around the pumping well water level is decreasing. Okay, this is the radius of radial flow. Okay, consider steady radial flow, let H is the depth of the flow at any radial distance R. This is, consider a small element. Okay, very small element, consider a very small element. The depth of flow at any radial distance R. So this is H, the depth of flow at any radial distance R. Depth of flow at any radial distance R. At any radial distance R. Okay, A means area of the flow, 2 pi RH for this pumping well. V, velocity of the flow. Okay, velocity of the flow. Now the discharge, very well known discharge. Okay, we know, all of us know this formula from third semester fluid mechanics. The discharge Q into the well is given by Q is equals to AB, continuity equation. Okay, according to the Darcy's law. According to the Darcy's law. Already we know this equation from module 1 and 2. Please revise the previous concepts. So, what Darcy's law says, velocity V equals to K into dH by dr, coefficient into hydraulic gradient. Okay, now just substitute the values into this equation. Q is equals to area, we know area 2 pi RH, okay, and velocity K into dH by dr. Area 2 pi RH and velocity K into dH by dr. Just rearrange the following, this term. Okay, H into dH. Okay, H into dH is equals to Q divided by remaining terms. So Q 2 pi K divided by 2 pi K, and arrange this term dr by R. When the radial distance R, the depth of flow is H1. See carefully in the diagram, when the radial distance R1, the depth is H1. When the radial distance R1, the depth is H1. So this is what boundary conditions. Okay, these two are boundary conditions. Okay. When the radial distance r1, the depth of flow is h1. When the radial distance is r1, the depth of flow is h1. Similarly, when the radial distance is r2, the depth of flow is h2. Okay. Here, depth of flow h1 when radial distance r1, depth of flow h2 when radial distance r2. Just substitute here. These are the boundary conditions. Okay. Just integrate this equation. Integrate this equation. Integration h dh between the limit h1 to h2 equals to 2 pi k constant, take outside, integration of dr by r, integration of dr by r between the limit r1 to r2. Now very simple integration. Integration of h into dh, integration of h is h square by 2, h square by 2 between the limit h1 to h2 equals to 2 pi k into integration of 1 by r, correct? Integration of 1 by r ln r between the limit r1 to r2. Just substitute the limits. 1 by 2 take outside, h square, so h2 square upper limit minus lower limit h1 square, that is equals to q divided by 2 pi k into ln r2 upper limit minus ln r1. Okay, here 2 get cancelled. Okay, form the equation for q. Q is equals to this term h2 square minus h1 square into pi k divided by ln r2 minus ln r1, log a minus log b form, log a by b. So ln r2 by r1. Just now convert the ln to log. Pi k same, h2 square minus h1 square same. So ln converted into log multiplied by 2.303 log of r2 by r1. Okay, this is the equation for radial flow in unconfined aquifer. Study radial flow in an unconfined aquifer. This is the equation. Okay, if there is no observation well, if there is no observation well, in the absence of observation well, just change the terminology. Okay, there is no observation well, only pumping well is there. So q is equals to pi k, replace h2 by h, replace h2 by h, total head of the water, h square minus h1, nothing but now hw, this one. There is no observation, please remember, there is no observation well. This is the equation, steady radial flow in case of unconfined aquifer. If there is no observation well, replace h2 by capital H and h1 by hw. Everything same, divided by 2.303 log of r2, radius of influence r2. This term is replaced by capital R, radius of influence, this one, up to the cone of depression, divided by r1. This r1 is replaced by rw. This is rw, radius of the pumping well. Okay, this equation is known as Dupit's equation. If there is an observation well, then this is Thiem's equation, or steady radial flow in case of unconfined aquifer. This is Thiem's. Okay. Thiem's equation. If there is no observation well, in case of there is no observation well, then this equation is called Dupit's equation. Okay, R nothing but radius of influence, this one, from the center of the pumping well to the end of the cone of depression, that is influence, radius of influence. H is head of water, H is head of water, full head of water. Okay, HW, water level in the well, this one. There is no observation well, please remember that point. HW means water level in the pumping well. Okay, HW, water level in the well, RW, radius of the well, this one. RW is the radius of the well, pumping well. Okay, and this is all about steady radial flow to a well in an unconfined aquifer. This is important. Okay, unconfined aquifer, sometimes also called as Thiem's equation. Okay, if there is no observation well, then the same equation is replaced by some terminology, then we call it as Dupit's equation. Okay. Yes, next derivation, steady radial flow to a well in a confined aquifer. Okay, steady radial flow to a well in a confined aquifer. Previous one is steady radial flow to a well in an unconfined aquifer. Now the same procedure for confined aquifer. The previous diagram also looks like this only. Carefully observe, in case of confined aquifer, as the name itself is suggesting, this is confined. There are two impervious layers. So this area, this water is confined between two impervious layer. Okay, two impervious layer. In the previous derivation, only one impervious layer, because that is unconfined and water level is open to atmosphere. But here the water level is confined between impervious layers. So, okay, this is impervious strata, impervious layer. Okay, this is important. And the thickness between the two impervious layer is B. Thickness between the two impervious layer is B. Okay. Same, this is pumping well, observation well 1 and 2, very similar to the previous one. Okay, height of water, head of water in observation well 1, H1, head of water in observation well 2 is H2. Okay, the radial distance from the center of the main well, pumping well, to the observation well 1 is R1. From the center of the pumping well to the observation well 2 is the radial distance, R1, R2. Okay. Head of water in the pumping well is HW. Okay, radius of the pumping well RW, very similar to the previous one, except this, in this case the water is confined between two impervious layer, because the name itself is suggesting this is for confined aquifer, previous one is for unconfined aquifer. Okay, this, and in case of unconfined aquifer, water level is open to atmosphere. Okay, but here virginal piezometric surface. Okay, one difference, and this one is the second difference from the previous one. Drawdown curve. Okay, cone of depression. Once the pumping starts, water level slowly decreasing, and this is the drawdown level. Water level decreased by some amount. In the observation well, it is observed S1. In case of observation well, it is observed as S2. Okay, same in case of pumping well, SW, drawdown. Okay, except this point and impervious layer, confined between two impervious layer. So except these 2 points and everything, rest of the thing similar to the previous derivation. Okay, in the previous derivation, area of the flow is 2 pi r h, but here 2 pi r b, because the thickness between impervious layer is B. Okay, and radius of influence R, radial distance R at corresponding head H. Okay, now consider the steady radial flow. Okay, very similar to the last derivation. H means depth of the flow at any radial distance R. H is depth of the flow at any radial distance R. Depth of the flow H at any radial distance R. Area of the flow 2 pi RB within this area. 2 pi RB. Thickness between the impervious layer is B. V, velocity of the flow. Very similar. Area is different. In the previous derivation it is 2 pi RH. Now it is 2 pi RB. 2 pi RB. The flow around a well penetrating fully into the confined aquifer. Here the flow around the well penetrating fully, okay, penetrating fully into the aquifer, confined aquifer of thickness B. This is of thickness B. Here thickness is B. Under steady state flow, yes, under steady state flow is shown in the figure. Now the discharge flowing into the well through a section, consider a small section, okay. This is, consider a small section of radial distance dr and height is dh. Discharge flowing into the well through a section which is situated at a radial distance r, is given by Q is equals to AV. Q equals to AV, A we know 2 pi RB and velocity according to the Darcy's law, K into dH by dr. Now just substitute the values, area 2 pi RB into velocity. This is Darcy's equation, correct? Very similar to previous one, Darcy's law, K into dH by dr. Now rearrange the terms, dH is equals to all this term divided by, just rearrange the term, dH is equals to, just rearrange the term, dH is equals to dH is equals to Q by 2 pi bk into dr by r, just rearrange the term. We know boundary conditions. At a radial distance r1, depth of flow is h1. At radial distance r1, okay, the depth of flow is h1. At radial distance r1, depth of flow is h1. Similarly, for the second boundary condition, at radial distance r2, the depth of flow is h2. At radial distance r1, depth of flow is h1. At radial distance r2, the depth of flow is h2. Substitute, integrate this equation between this boundary condition. Integration dH between limit h1 to h2 equals to Q'd by 2 pi bk outside, constant treated, okay, take outside. Integration of dr by r between limit r1 to r2. Okay, now very simple integration. Integration of 1 into dh is h. Integration of 1 into dh is h between the limit h1 to h2. Now upper limit minus lower limit, h2 minus h1 equals to q divided by 2 pi bk as it is, multiplied by integration of 1 by r dr, correct? Integration of 1 by r dr, very similar to previous one. And this was simple integration, we must know. Integration of 1 by r dr is ln r, okay, ln r between limit, okay, between limit r1 to r2, between limit r1 to r2, just upper limit minus lower limit, ln r2 minus ln r1. Now rearrange the terms. Q is equals to 2 pi bk into h2 minus h1 divided by ln r2 minus ln r1. Okay, log a minus log b, nothing but log a by b. So in that form, just simplify this term. Ln r2 by r1. Now Q is equals to, and we know B into K is nothing but transmissivity, correct? B into K, T, transmissivity T, B into K. This is what? Transmissivity. Transmissivity, just replace B into K by T, 2 pi, Bk nothing but T, H2 minus H1 divided by ln, convert that into log 2.303 into log of R2 by R1. This is steady radial flow to a well in case of confined aquifer. Simply we can call this as Thiem's equation for confined aquifer. Thiem's equation for confined aquifer. Don't get confused. Previous derivation also we said Thiem's equation. That is Thiem's equation for unconfined aquifer. Okay, this is Thiem's equation for confined aquifer. Okay, don't get confused. Okay, we can say in that fashion also. Previous one is steady radial flow for unconfined aquifer, nothing but Thames equation for unconfined aquifer. This is steady radial flow in a confined aquifer, nothing but Thames equation for confined aquifer. Okay, this is Thames equation for confined aquifer. Now, in case of absence of observation well, if there is no observation well, only pumping well is there. Now just similar to the previous one, replace the terms because there is no observation well, so these terms are replaced by these terms. Okay, 2 pi t as it is, H2 means H1, okay, replaced by H, total head, H, and H1 is replaced by HW, whole divided by 2.303 log of R2, radius of influence is replaced by R, capital R, radius of influence, capital R, divided by R1 is replaced by R1, means this is radial distance R1 because there is no observation well na. So simply it is replaced by RW, radius of well. Now 2 pi t as it is, H minus HW is replaced by, okay, H minus HW is replaced by this term, H minus HW is replaced by SW. Draw down, listen, H minus HW, nothing but draw down SW, correct? This is H, from here to here it is H. H minus HW, you will get SW, draw down. So this term is replaced by SW divided by same thing, 2.303 log of R by RW. Okay, this is means SW nothing but drawdown in the well. This is the Thames equation for confined aquifer. This is modified one. In case of there is no observation well, this is the final result. And again we can call this as Dupuit's equation. Okay, the concept almost similar. Okay, for unconfined aquifer and confined aquifer. Here the water is confined between two impervious layer and area is 2 pi b, 2 pi rb. In unconfined aquifer that is area 2 pi rh. Here 2 pi rb. Okay, everything very similar, don't get confused. So up to here this is a steady radial flow for confined aquifer, okay, or nothing but Thames equation for confined aquifer. If the terminologies are modified, nothing but there is no observation wells, then the same equation becomes like this. Okay, this is Dupuit's equation. If there is no observation well, that becomes Dupuit equation. If there is an observation well, that becomes Thames equation. If there is no observation well, Dupuit's equation. Okay.